Hi, my name's Bonnell-Kangas. I'm an electrical and computer engineering student here at The Ohio State University, and one of the technical coordinators for Buckeye Current, the electric motorcycle team at the Ohio State Center for Automotive Research. I want to talk to you today about the product I've been working on for the last 8 months and my entry into the 2014 TI Innovation Challenge, the Battery Interface Module. First, a little bit about the team. Buckeye Current is a student project team that designs, builds, and races electric motorcycles. Last year, our motorcycle RW2 took 3rd place in the 2013 Isle of Man TT0, one of the most prestigious motorcycle races in the world. The 2 competitors that took 1st and 2nd were multi-million-dollar professional teams. If there's one thing the team has a lot of, it's batteries. Pretty much the entire volume of the motorcycle's chassis is filled with batteries. Actually, we have 110 of them in this year's bike, and they're all connected together in one big series string. It's one of the most expensive parts of the vehicle, and one of the places where the most of our design attention goes. You might know that lithium batteries are kind of finicky. Among other things, they really don't appreciate being overcharged or over-depleted. So, in contrast with, for example, a lead-acid battery, where you can pretty much ignore the fact that you have a 6-cell string, with a lithium string you really should monitor every individual cell voltage and probably their temperatures too. But that task is a little more difficult than it sounds. Our cell circuit is 110 series cells, and that's over 450 volts when they're fully charged. Let's say you try to measure 6 of those cells with a 14-bit ADC and a voltage divider. All of a sudden you're down to about 1.6 millivolts a bit, and your resistor tolerances and your matching starts to get kind of expensive. Fortunately, TI makes this device called the BQ76PL536A, which makes your life a lot easier. The 536 is a 6-cell battery voltage monitor with a bunch of useful features. It measures 6 series cells and measures their voltages, has a couple of thermistor inputs so you can measure their temperatures as well, and it communicates with a unique interface, current mode SPI, up and down a daisy-chained series of these devices, which we call a stack. The 536A makes the design of this board a lot easier, and it makes measuring this kind of series string a lot more convenient. The battery interface module is an integrated 36-cell battery monitor that's powered off the vehicle's 12-volt bus and can communicate on the vehicle's CAN bus. It's based around the PL536 and the TI C2000 Piccolo processor. Let's have a look at some of the components and the features of the board. The board is divided into a high voltage and a low voltage side for safety. Here on the high voltage side, we have a stack of 6 BQ76PL536A devices. These devices communicate with an SPI current mode interface up and down the stack. The only one that communicates with the host processor is the base device here. Here on the boundary between the high voltage and low voltage sides, there are 2 isolation chips, the TI ISO 7241C. The 7241s are a really beefy 25 megabit per second digital isolator that allow us to have communication across this boundary between ground planes without actually having an electrical connection. Across the boundary on the low voltage side, we have the Piccolo, the TMS 320 F28035. This is the processor we use on all of our CAN nodes here on Buckeye Current, and it's proved really great for us because we have as much processing power as we need, plenty of onboard flash, as well as a built-in CAN module that handles a lot of the sending and receiving of CAN messages in the background. Actually, physically sending and receiving the CAN messages is handled by a CAN transceiver on the opposite side of the board, the TI SN65 HVD230. Normally there are 2 big sealed connectors there on the board, but I've taken them off so you can look at the power supply for this board. All of the CAN nodes are powered off of 12 volts from the vehicle's low voltage battery. In order to get the 3.3 volts we need for the processor, we use this switch mode power supply. It's actually a DC to DC converter. It's the LMR 14206. The LMR is really nice because it gives us 4.5 volts to 42 volts of input voltage and as much output current as we need on the 3v3 side. And that really frees us from having to worry about our input voltage if our battery is sagging too low or if somebody's overcharged it. We don't have any concerns about frying our input. At other times in the team's history, we've used integrated DC to DC converters, like some of the ones that are drop-in replacements for the 7803 series, the linear regulators. Those are really convenient, but it also adds a lot of unit cost to the board. This entire power supply circuit is implementable for $1.50, $2 in components, whereas just one of those integrated DC to DC converters costs almost $10. That's a big savings, even as soon as we start talking about 10 or 15 boards. You might have noticed this big electrolytic capacitor here next to the power supply circuit. That's not a filtering capacitor, it's actually acting as something like a backup battery for the circuit. On the other side of this diode here, there's a voltage divider connecting the 12-volt input to a comparator on the C2000. When 12-volt power is removed from the device, or when the bike is turned off, this capacitor keeps the C2000 alive long enough for the comparator to trip and the C2000 to command all of these BQ devices to enter a low power state. This prevents excessive current drain from the cells that we're measuring if the bike is left in storage for a period of up to 2 months. I've now finished building and testing 7 battery interface modules. 5 of them will be installed on RW2X, the team's 2014 race vehicle, for the 2014 TT0 on the Isle of Man. The team uses data from the battery interface module to diagnose and monitor the powertrain, including balancing the battery pack and identifying bad cells before they cause us issues during the race. Data about the cell's performance is stored and used to help inform the design of the next year's race vehicle. While the modules have already undergone several weekends of high-speed, on-vehicle track testing, the real test comes on the course at the Isle of Man. The 2014 TT0 is on June 5th, so watch out for us there, or on the team's website at current.osu.edu. You can find schematics, PCB layouts, and a detailed description of the battery interface module design on my GitHub page, which is linked in the video description. Until then, thanks for hanging out.